This is section 8.1a, Introduction to Matrices. A matrix is a rectangular array of real numbers. Matrix A has 2 horizontal rows and 3 vertical columns. So here we have a sample matrix A, and it's usually indicated with brackets, sometimes with longer parentheses, but usually brackets. And we can see a bunch of numbers here, 3, 1, -2, 7, -1, 0.5. An arrangement or array of numbers like that, that's in the pattern of rows and columns, is called a matrix. So this is matrix A. It has 2 rows and 3 columns. Each entry can be identified by its position in the matrix. So 7, for example, in matrix A is in row 2, column 1. -2 is in row 1, column 3. So when you're describing the position of a matrix element, you always specify the row first and the column. A matrix with m rows and n columns is of order m by n. So most of the screen is just to make sure that you understand the terminology for dealing with matrices. And matrices have order. And the order is the number of rows by the number of columns, so m by n. The matrix A that we showed at the top of the screen is of order 2 by 3 because it has 2 rows and 3 columns, so it's a 2 by 3 matrix. A is a 2 by 3 matrix. If m equals n, that is, the number of rows equals the number of columns, then we are said to have a square matrix, And it's easy to remember that because if you look at a square matrix, it looks square because the number of rows equals the number of columns. Here's some examples just to make sure we understand the terminology. Find the order of each matrix. This is matrix A, 2, 3, 1, 0, 4, 2, 1, 4, 1, 1, 6, 2. What's the order? Well, you should quickly give me that order, write it down, and I'll give you a second to do that right now. You should have come up with 3 rows, 4 columns, and therefore the order of A is 3 by 4. A is a 3 by 4 matrix. How about this matrix, B? What order is B? Quickly write it down. B has 1 row and 5 columns, therefore it is a 1 by 5 matrix. The order of B is 1 by 5. B is called a row matrix just because it has only 1 row. Also, a matrix that has only 1 column is called a column matrix. Matrix C, 3, 1, 6, 2. Quickly write down the order. Yes, it is a 2 by 2 square matrix. A 2 by 2 square matrix. And of course, we call it square because it has the same number of rows as columns. An m by n matrix can be written A equals brackets Aij equals, and then you can write down what's in brackets there. Don't be intimidated by all these symbols. It's really just a general way of writing a matrix. And the only reason I'm showing you this is just so that if you ever do see a matrix written this way, you know what it means. Let's start with the upper left corner of this matrix where you see A11. Those subscripts simply mean first row, first column. A12 going on just means first row, second column. And then the ... because we don't know how many elements we have per row. That subscript 1n just means first row and nth column, whatever n is. Again, this is a general way of writing, so we're not specifying the order. On the second row, A21 just means second row, first column. A22, second row, second column, etc. until the end. A2n means second row, nth column, nth column. Skipping down now to our last row, AM1. We don't know the number of rows m, but we do know that the very last row is going to be M1 because it's the mth row, first column. It's kind of hard to say mth, mth, mth. The mth row, first column, and then AM2 is the mth row, second column, then dot, dot, dot. The very last element, AMN, is in the mth row and nth column. The mth row and the nth column. Anyway, this isn't that important. It's just so that you can recognize matrices if you ever see them written this way. And the other important thing is just to realize that the subscripts I, J, I always stands for row, and J always stands for column. Two matrices, A equals Aij and B equals Bij, are equal if they have the same order, and Aij equals Bij for every I and J. Alright, that's a fancy way of saying a simple thing. For example, these two matrices, 0.5, root 9, 147, and 1/2, 3, 0.257. These are equal matrices. They're equal matrices because they have the same order. They're both 2 by 2. And all corresponding entries are equal. Look at 0.5, for example. Well, 0.5 equals 1/2. Or look at root 9. Root 9 equals 3. Or look at 1/4. 1/4 equals 0.25. So these two matrices are equal. And it's important to remember that only matrices of the same order can be equal. An augmented matrix and a coefficient matrix are associated with each system of linear equations. Again, we're just trying to learn terms here because these terms are used when dealing with matrices. For example, this is a system, much like the systems that we learned in the last chapter. 2x plus 3y minus z equals 12, x minus 8y equals 16. Every system has a matrix associated with it, and this is one of the main reasons we're learning about matrices is because they are going to help facilitate the calculation of every system that we might encounter. So the augmented matrix associated with this system is 2, 3, negative 1, 12, 1, negative 8, 0, 16. Notice the dotted lines in there. The dotted lines really just separate the coefficients from the constants on the right side. In the future, you're not going to need to write the dotted lines. I'm not going to require that. But if you do see dotted lines, just know what it means. It's just a way of separating the coefficients from the constants. It's really not that important. So the augmented matrix is this. Now, where do we get it? Well, you can see that the coefficient of x in the first equation of this system is 2. I'm talking about the row 2x plus 3y minus z equals 12. Well, the coefficient of x there is 2. Therefore, we write 2 in the matrix. Coefficient of y is 3. Therefore, we write 3 in the matrix. And the coefficient of z is negative 1. Therefore, we write negative 1 in the matrix. And, of course, the 12 at the end. So you can also see where we get the second row of this matrix straight from the system. Notice that in the second equation of this system, there is no z term. Therefore, as a placeholder, we put a 0. We put a 0 in the matrix. It's important to represent everything, even terms that aren't there. So we put a 0 there. The coefficient matrix is 2, 3, negative 1, 1, negative 8, 0. And as you can see, that's really just the coefficient portion of the augmented matrix. Again, this is just so that you know what a coefficient matrix is. But for most of our work, we're going to be dealing with augmented matrices. Now we're going to solve a system of equations using a matrix. And this is one of the main reasons that we are learning about matrices, because they're very useful for solving systems. Now here's a system like what you have seen a lot in the last chapter, Chapter 7. And we see x minus 4y plus 3 is equals 5, negative x plus 3y minus z equals negative 3, 2x minus 4 is equals 6. And we can write this as a matrix. That matrix would be 1, negative 4, 3, 5, negative 1, 3, negative 1, negative 3, 2, 0, negative 4, 6. And you can clearly see where we got those numbers from. We just got them from the coefficients and constants in the system of equations. So the reason to use a matrix is because it makes your calculation easier. You don't have to write all those x's and y's every time, or you don't have to write all the equal signs. So it does, cut down on the time it takes to calculate matrices. Now you already know how to do Gaussian elimination, so for practice, you should pause the video and do this on your own. If you find that you get stuck, that's okay, because this is the first matrix that you're solving by Gaussian elimination. So if you get stuck, just resume the video until you get unstuck, and then when you finally have an answer, you can watch the entire solution of this matrix. So our first step is to add row 1 to row 2. We are adding row 1 to row 2, and that will give us a new row 2 of 0, negative 1, 2, 2. Our next step is going to be to multiply row 1 by negative 2, and we're doing that because we want to eliminate the x term in the third row. But first, we need to multiply the first row by negative 2. And so we got negative 2, 8, negative 6, negative 10, 0, negative 1, 2, 2, 2, 0, negative 4, 6. Now, we can add row 1 to row 3, and we end up with this matrix, negative 2, 8, negative 6, negative 10, 0, negative 1, 2, 2, and the now modified third row, 0, 8, negative 10, negative 4. And we can see we are getting closer to row echelon form. Well, my next step, since I want to get rid of the y term in the third row, my next step is going to be to multiply row 2 by 8. And so I'm going to end up with negative 2, 8, negative 6, negative 10, 0, negative 8, 16, 16, 0, 8, negative 10, negative 4. And you can clearly see why we did that, because we want to eliminate that y term in the third row. So my next step at this point is to add row 2 to row 3, and this is what I'm going to get. I'm going to get this matrix, negative 2, 8, negative 6, negative 10, 0, negative 8, 16, 16, 0, 0, 6, 12. And of course, the last step in order to get the row echelon form is to multiply each row by the appropriate constant. So I want to multiply that first row by the constant negative 1/2, because that'll give me 1 as my x coefficient. I'm going to multiply the second row by negative 1/8, because that will give me 1 as my y coefficient. And I'm going to multiply the third row by 1/6, because that will give me 1 as my z coefficient. And I end up with 1, negative 4, 3, 5, 0, 1, negative 2, negative 2, 0, 0, 1, 2. And this matrix is in row echelon form. And just as we did in Chapter 7, we can easily solve for the variables now. I see that z equals 2. From the last row, 0, 0, 1, 2 tells me that z equals 2, and then I just use back substitution. And my final answer is z equals 2, y equals 2, x equals 7. That is the correct solution to this system of equations, which we have now solved using a matrix and Gaussian elimination. Another example, write the following system as a matrix and solve by Gaussian elimination. X plus 3y minus w equals 3, negative y plus 4z plus 2w equals 18, x minus 5z minus 6w equals negative 38, 2x plus 4y minus 3z equals 1. As you can see, this system's a little bit more complicated, but we're going to be following the same strategy. So I'll get you started and give you this matrix. This matrix is simply the system written in a different way as an augmented matrix. And we have the coefficients, 1, 3, 0, negative 1, 0, negative 1, 4, 2, etc. The coefficients and the constants all written together in the same matrix. So it's very similar to what we did in the last example. Now, I'm not going to go through every single step for the calculation here, but I am going to show you the strategy to follow. And you'll see in a minute that it makes sense. Okay, well, we know that we would like to get this into row echelon form. And row echelon form has all ones on that diagonal of coefficients. Like, you know, for example, what we found on the last screen. So row echelon form is nothing new to you. And so the strategy to follow is, first we're going to try to get this number. It happens to be a 1 in this matrix, but it doesn't matter what the number is. We want to get that number to be a 0. So we're going to do the necessary row operations to achieve that. After we get that number to be a 0 by modifying the third row with whatever row operations I do, I'm then going to try to get this number in the resulting matrix. I'm going to try to get this number to be a 0. So I will need to modify row 4 by doing the necessary row operations. After I do that, I'm going to try to get this number to be a 0. You can see what we're trying to do here is step by step get towards row echelon form. So I do the necessary row operations to make this number 0, and finally, in the resulting matrix, I will do the necessary row operations to make this number a 0. Okay, and once I do that, I'm going to have all zeros in the lower left portion of the matrix, and the matrix will then be in row echelon form. So now is a moment to apply all that you've learned. You do have all the tools necessary to do Gaussian elimination on this matrix. I already gave you the strategy. So pause now, do this on your own, do it carefully. Recall that it's easy to make little arithmetic errors with matrices. So do it carefully and then resume the video when you have an answer, or of course if you get stuck and you need the help. So pause now and do that. The final answer, w equals 4, z equals 3, y equals 2, x equals 1. That is the final solution to this system, which we have solved with Gaussian elimination. The classwork, page 582, please copy these numbers down, and we'll work on them in class.